So I'm just going to do a couple of more questions and then we can move on. Like for example, this question over here. You have an industrial process. Two gases, X and Y, react together to form a single gaseous product. So here's your, let me open the marker. So here is your reaction that's given. You're being given the percentage yield of product Z varies according to the pressure and the temperature as shown in the graph. So there's a graph given. And now, if you look at the equation, you would know that if you increase pressure, less gas moles side is favored. So that is going to be the forward reaction in this case. So forward is going to be favored if you increase pressure because the forward has fewer gas moles. And you can see this over here as well, that if you're increasing pressure, I mean, this is the direction in which the pressure is increasing. Learn to interpret graphs as well. The amount of Z or the percentage of Z is going up, right? All of the graphs, it's rising. So as you increase pressure, more forward reaction, more Z is produced, less gas mole side is favored. And based on this graph, we're going to figure out whether this reaction is endothermic or exothermic. So we're going to try and I mean, I'm not even going to look at the options right now, TK, whether the options have anything to do with this or not. I'm just trying to figure out how to interpret the graph. So the other thing is, I mean, the graph gives you a relationship between pressure and the percentage of Z, and it also gives you a relationship between the temperature. So the temperature is going down, right? I mean, there are multiple graphs given. So your temperature is decreasing. Your temperature is decreasing. But what's happening to the amount of Z? Like if you have a lower temperature, 373 kelvins, then the amount of Z is almost 100%. And if you have a higher temperature, the amount of Z is much lesser. So if you decrease temperature, more Z is formed. I mean, that's the other information that we can derive from the graph. More Z is formed, more forward reaction is going to happen. More Z is going to be produced. Whenever you decrease temperature, which reaction is favored? It's always the exothermic reaction that's going to be favored. So that means the forward reaction is the exothermic reaction in this particular case. The Usman, we haven't taught equilibrium constant. We just started equilibrium. So, I mean, that's what we're going to probably start in this class. Okay, we're going to learn how to figure out equilibrium constants. So, we're just starting we just did the first topic, subtopic. So the reason I wanted to do this question was that you need to interpret this graph and figure out which one is the exothermic, which one is the endothermic reaction. I mean, you could be asked multiple things. I mean, by just looking at the graph, you can figure out whether the forward reaction is exothermic or endothermic. So your temperature decreases, but the amount of Z produced actually increases. So that means more Z is formed. That means more forward reaction happens. And whenever you decrease temperature, the rule is that the exothermic reaction is always going to be favored. So the forward reaction in this case, although they haven't told us, but we have figured out that the forward reaction is the exothermic reaction or vice versa. The backward reaction is your endothermic reaction. Now, which statement about this equilibrium cause reaction is correct? So decreasing the temperature decreases the value of the equilibrium constant. We haven't studied equilibrium constant, so forget that. Decreasing the temperature increases the rate of the reaction. That's obviously incorrect because if you decrease temperature, all reactions would slow down, whether it's the forward or the backward. Remember, this particular statement was not about equilibrium. Be careful. It was about the rate of reaction. Increasing the pressure increases the value of the equilibrium constant. Uh, We haven't studied equilibrium constant. The last statement is the correct statement, which we figured out initially by just interpreting the graph. Okay, is this question clear? Everyone? Usman, Rida, Sanjida, is this clear? Asha, so we're going to try and do uh, just one more. The dissociation of this Seth, they're saying that there's this equilibrium happening. N2O4 is breaking down to form 2NO2 in equilibrium. If the temperature of an equilibrium mixture of the gases increase at constant pressure, will the volume of the mixture increase or decrease, and why? So the question is, he's increasing temperature, right? And the question is that they are asking us to tell them what is going to happen to the volume. Again, it's like, I mean, this question could be interpreted in many ways. Now you're increasing temperature. The first thing is, where would the reaction uh, shift? Where would the equilibrium shift? So whenever you increase temperature, it's always the endothermic reaction that's going to be favored. And the enthalpy change is always given for the forward reaction. It's plus, so that means the forward is endo. And if you increase temperature, the endothermic is going to be favored. There's 1 mole of gas in the reactants, and the products there are 2 moles of gas. So the reactant has 1 mole of gas, and the product has 2 moles of gas. Now, what would happen to the volume and why? I mean, you're getting more moles of more forward reaction. That means more gas is being produced. So the volume should increase, right? So one of the reasons it's going to increase is reason number one, more moles of gas are produced. Is this part clear to everyone? Sajida, is this clear? Osman, Rida, is this clear? So you have more moles of gas being produced. Endothermic reaction would be favored. So more forward reaction in this particular case. But there's a second reason why the volume of gas, and the second reason has to do with physics. That has to do more with common sense. The second reason is that reason number two. I mean, they've actually given this in the options. Reason number two is why the volume increases. Whenever you heat a gas, whenever you increase temperature, there's going to be thermal expansion. Hopefully, I mean, we haven't done ideal gases, but physics, O levels. Whenever you increase temperature, gases expand. So there are two reasons. First one, more moles of gas are being produced. The second reason is at a higher temperature, gases would be more energetic. They would break the intermolecular forces and they would be further apart and they would expand. So the volume will increase both because of a shift of equilibrium towards the right and also because of thermal expansion. So both reasons are going to be in play. Uh, so that was, I mean, there was this extra point in it which you had to look out for. Okay, is this clear to everyone? I said then you have, okay, then you have, there's this question and they're asking, I mean, there are two bulbs, R and S. Coming to the right to the question, when the temperatures increase, which gases in bulb R would cause the mercury level in the right hand limb of the manometer to rise? So, right hand limb. This is the right hand limb. He wants the right hand limb of the mercury to rise. Then that obviously means that the left hand limb would be going down. Why would it be going down? Because I mean, there's probably more gas over here. and more gases would be pushing the mercury from one side, which is why it's rising from the other side. So so there's something that's going to happen, that there's going to be more gas over here. Like whatever you do when the temperatures increase, so you're increasing temperature. Now you're increasing temperature. So if you increase temperature, more gas should be produced. Remember, you're increasing the temperature of the whole thing, of the whole apparatus. So thermal expansion is not an issue here, because if this gas expands, this gas would also expand. So that's not an issue. You need more gas. More gas would push the level down over here. Uh, so in this case, the first reaction, it's positive, it's endothermic. Forward is endothermic. So the forward reaction is endo. So whenever you increase temperature, which reaction would be favored? Endothermic would be favored. And you can see more gas would be produced. So he's saying what could be present in R. So if this equilibrium mixture is present, then this is what's going to happen. That if you increase temperature, then all of a sudden there's going to be more gas because the equilibrium would shift in the forward direction, and there's going to be more gas, and more gas would push this equilibrium downwards. The second one is not going to be true because it doesn't matter whether the equilibrium shifts to the right or it shifts to the left, because on both sides you have equal moles of gas. So the quantity of gas is not going to change. Uh, so it doesn't really matter. If you increase temperature, you still have the same amount of gas over here. You decrease temperature, you still have the same amount of gas. 1 mole changes into 1 mole of some other gas, doesn't really matter. And the last one is that nitrogen. If you have nitrogen over here, then that's obviously nothing would happen because you have nitrogen over here and you have nitrogen on the other side as well. So both gases would expand equally. There is no equilibrium, so they're going to push the mercury equally, and no significant change would happen to the mercury. So only option number one would be correct in this particular case. Okay, is this example clear as well? Yes or no? Is this clear? So just very quickly, I'll just do one more graph question. You can remember interpretation of the graph. Now, they're talking about the Haber process, although we haven't done Haber process. It's part of inorganic, but from O levels, you know what the Haber process is: N2 plus 3H2. It's in equilibrium with two NH3s, and they're all gases. And the forward reaction is exothermic. You can remember that it's exothermic. Backward would obviously be endothermic. On the left side, you have more moles of gas. I mean, if the reaction shifts backwards, it's more gas produced. I mean, there are 4 moles of gas. And in the product, you have 2 moles of gas. So there's less gas. So he's asking us, what is he asking? He's asking that two separate graphs are plotted, one at 400 and one at 500. Which one, first thing, which one would have more percentage of ammonia? And now the graph has to be interpreted in two ways. One is the relationship between temperature and the percentage of ammonia, and the other one is what would happen if the pressure is, I mean, in this direction, the pressure increases. So first thing, I need to figure out whether the graphs would be moving upwards. Would we get more ammonia, like A and B, option A and B? As pressure increases, you get more ammonia. Forget the temperature. The graphs are rising. As pressure increases, you get more ammonia. The other one is, as pressure increases, you get less ammonia. So we're going to figure this out. Higher pressure. Which side is favored? Less gas moles. At higher pressure, less gas is going to be produced, which means more ammonia because the forward reaction would be favored. So that means as the pressure increases, the amount of ammonia would increase as well. So it's either A or B. So these two are definitely incorrect. The second option is, now you have to figure out the relationship between temperature and the amount of ammonia. Like at 500 degrees centigrade, this graph is suggesting that you're going to get more ammonia, and the 400 degrees centigrade graph is lower, so that means you're going to get less ammonia. So higher temperature, lower temperature. Let's try and figure out what would happen with temperature. So higher temperature, if I keep a higher temperature, which in this case would be 500 degrees centigrade is your higher temperature. What's going to happen at higher temperature? Endothermic would be favored, right? And endothermic is the backward reaction. So you're going to get less ammonia at 500. So that means the 500 graph would be actually lower. You're going to get less ammonia. At 400, you're going to get more ammonia. Hence, option A is the correct option. Okay, is this question clear? Yes or no? Is this clear? Okay, Usman, is this clear? So just remember that how to interpret Lee-Shatler principle can be tricky. I mean, you can get tricky questions. Uh, Most of the questions would be not as tricky, but they would be relatively straightforward. Uh, I think most of them. So we've done two graph questions, and that's so we can do the worksheet later. Uh, I mean, this one. Let's try this one. Just one more. Now, this question states that PCl5 decomposes, and it's decomposing 13% at 160, which means, uh, and it's 100% at 300. So temperature increases. Increase in temperature, more forward reaction happens. So basically, at at 160 at a lower temperature, it wasn't. I mean, this reaction wasn't going forward. But at a higher temperature, it is going forward. Although this is not reversible, but the rules still apply. If you increase temperature, the endothermic reaction is going to be favored, which means the forward reaction is the endothermic reaction. So the reaction is, I mean, it's either going to be A or C. So we can now move on to the next thing. Okay, I'll send you the worksheet. So I'll send you the worksheet for Lee-Shatler principle, and we can move to the next thing, which is equilibrium constant. Like if things are at equilibrium, so we can start talking about equilibrium constant. The first thing that we're going to talk about is called Kc. And we need to figure out what is this. One thing that I initially told you was, for example, if I have a reaction and there's a container and the reaction is going on. I mean, we did the water examples. Let's do some other example. We have a container, and that container has H2 and Cl2 reacting to form HCl, two molecules of two molecules of HCl. So there's going to be forward reaction. So initially, let's I mean, the red dots are H2, the green dots are Cl2, and the blue dots are HCl. So I'm going to add two blue dots. I mean, two molecules of HCl are produced. So let's say initially I added just H2 and lots of H2s, lots of Cl2s in my container. So only H2 and Cl2 are present. So what's going to happen is two of them are going to collide with each other. They're going to combine and they're going to form HCl molecules. So initially, and this is a reversible reaction, but initially only forward would be possible because there is no HCl. So backward would not be happening. So H2 and Cl2 would combine and they would change into two HCl molecules. So you get two HCl molecules. So that's the first reaction. Then more H2 and Cl2 would react with each other. So these two would collide with each other and they would react and they would form two HCl molecules. So you're going to have more and more. You're going to have more and more HCl molecules forming. So forward reaction starts happening. Let's say that a few more H2 and Cl2 molecules react and they produce two HCl molecules. H2 and Cl2 react. And then once this happens, backward reaction will also start happening. Then the reaction would start going in the forward and the so two more H2 and Cl2 molecules react and produce HCl, but at the same time, two HCl molecules might combine to form H2 and Cl2 back again. So they might combine to form H2 and Cl2 back again. And that's when a reversible reaction sets in. And there's going to come a point when the rate of forward reaction and the rate of backward reaction would be equal and the reaction would be at equilibrium, which means that the net quantity of the reactants and the products would stop changing. I mean, the reaction would still be going on, both forward and backward, H2 and Cl2 combining to form HCl, and vice versa, HCl breaking down to form H2 and Cl2. So rate of forward reaction and rate of backward reaction becomes equal. Equals rate of the backward reaction. So the reaction is going to be at equilibrium. Now remember, the thing that we are talking about, Casey, that is only applicable to reactions that are at equilibrium. Okay, I'm just going to warn you that if a reaction is not at equilibrium, you can't use the word Kc or you can't measure Kc. So first thing, Kc is only applicable. So Kc is only applicable to reactions that have already attained equilibrium. Okay, that's one very important thing to remember. Then you have, and now I'm going to tell you what Kc actually is. So Kc is that once the reaction reaches equilibrium, the products are going to have a particular concentration and the reactants are going to have a particular concentration. Sometimes you're going to get more products depending on the conditions, and sometimes you're going to get more reactants depending on the conditions. But whatever happens, if the reaction reaches equilibrium, then the amount of products and the amount of reactants, they would stop changing. So the concentration of the product and the concentration of the reactant would stop changing, and they're going to have a ratio. I mean, if it could be that the concentration of the product is higher and the concentration of the reactants are lower, then you're going to get a ratio which is called equilibrium constant, Kc, and it's going to have a larger value. Or vice versa, the equilibrium might be reached at a point when the reactants have a higher concentration and the product have lower concentration. In that case, Kc is going to have a lower value. So the reactant concentration would be higher and the product concentration would be lesser. And this ratio, the ratio of the concentration of the products divided by the concentration of the reactants, this ratio is called Kc. Okay? Is this clear, the idea of Kc to everyone? So So now taking this idea forward, how do you write the expression for Kc? Now, one thing that you must remember is whatever your products are, write down all your products. For example, in this case, it's HCl. The concentration of HCl. Remember, concentrations are written in square brackets. So that's your product. And the other one, your reactants. You have two reactants. One is H2, and the other one is Cl2. So you're going to write both of your reactants. And this is multiplication. A lot of people actually mistake this for addition, and you see a lot of these mistakes. So when you write the concentration of the products, write all the products and write all the reactants. Now, one thing that I did not write over here is that I had two molecules of HCl. Now, when you have two molecules of HCl in the expression for Kc, I mean you could have, if it's two molecules, then the coefficient becomes the exponent. You're going to write HCl squared. The reason you're going to write HCl squared is because one molecule is going to react with one molecule, and they're going to produce two molecules. So the weight of HCl, like if the reaction shifts forward, a lot more HCl is going to be produced. So HCl has a bigger weight. So you're going to write squared over here, and this is how you're going to write your expressions for Kc. And I'm going to write coefficient in the equation becomes the exponent. So the very first question that you're going to get is to write the expression for Kc. That's the first part of the question. Okay, always the first part of the question is going to be right. You're given an equilibrium reaction. You have to write the expression for Kc. Is this clear? Yes or no? No, you can't write 2HCl. The reason actually you write HCl squared is, I mean, if I what I can do is I can rewrite the equation. It's basically I can write two HCl molecules separately. So it's one HCl molecule and another HCl molecule. I mean, that's what your actual equation is like. So you have two HCl molecules. So it's a product concentration, it's HCl concentration. The other product is also HCl, so HCl concentration divided by the reactant concentration, which is Cl2, and the other one is H2. So it's basically HCl comes twice in your products. So it's HCl concentration plus HCl concentration divided by Cl2 concentration divided by H2 concentration. So that's your expression, which is why it becomes the coefficient actually becomes the power. So Gita, is this clear? Just so as far as this clear as well. Okay, now the next thing is, and the next thing I'm going to talk about is, and we're going to talk about the same expressions. Let's do another one. The first thing is learning to write. You have to learn how to write the correct expression. And remember, it's a constant. This equilibrium is always a constant. I mean, it's once something reaches equilibrium, the amount of products don't change, and the amount of reactants they also don't change. So the ratio would remain a constant. The product concentration and the reactant concentration, the ratio of the products divided by the reactants, it's going to be a constant. So let's do another one. Another one would be that I have this reaction N2 plus 3H2 and it's an equilibrium with 2NH3. Now what's the question is what's Kc in this case? the expression for Kc. So it would be product concentration, which is NH3, and I told you that that the coefficient becomes the power or the exponent. It's going to be NH3 squared divided by the reactants, which are N2, and the other one is H2, and the coefficient becomes the power, so it's going to be H2 cubed, and these two would be multiplied. Uh, or you can interpret it the other way around. I mean, this equation could be written as N2 plus 3H2, so that means H2, another H2, and another H2 in equilibrium with the product, which is two molecules of NH3, so that's NH3 plus NH3. So these are all your products. So if you write the expression for Kc, it would be NH3 concentration. The other product is also NH3, so that's multiplied by NH3 concentration, which is why it becomes squared. And you're going to divide it by N2 concentration into H2 concentration into the other reactant is also H2, so that that's H2 concentration, and then another H2 concentration. So it's going to come out to be the same expression that you're getting over here. So remember this, that the coefficient in the equation, it becomes the power in the expression. And this is what you're going to get. Is this clear? Yes or no? Is this clear? So then you have, so let's work on this just a little bit more. Quickly tell me what, I mean, you can type the answer actually even. Tell me what's the expression if SO2 is reacting with O2 and it's in equilibrium with 2SO3. And I'm going to give you another one as well. It's N2O4 in equilibrium with 2NO2. Or we can, so that's and number 3 as well. Tell me for all three. Send me a picture if you can quickly on WhatsApp. We can think of another equilibrium. So it's copper 2 plus Fe2 plus in equilibrium with Fe3 plus copper 1 plus. For all three, tell me what's the expression that's coming out. Tika, I'm waiting for the expressions. Send me the expressions quickly on WhatsApp. And sorry, my mic was off. Were you able to hear me properly? Say this quickly. I'm waiting for these three answers. The Kc expression for all three equilibrium. I mean, there's separate questions A, B, and C. So we want the Kc expressions. Okay, just try and do this very, very quickly. I said quickly. I think you should be done by now. Sanjida, it's yours. Sanjida, this one. I'm just going to have. I'm just going to quickly go through the last one that you sent. Why is it becoming squared? Remember, I told you that the coefficient becomes the power. I mean, in this particular case, you have this reaction that's happening. I mean, there's one mole. It's one Fe3 plus one CO2, one plus one Fe2 plus one copper 2 plus. So the Kc expression, if you're going to write, it's going to be Fe3 plus concentration, copper 1 plus concentration, products divided by reactants. So it's so let me just complete this. It's the other one would be copper 2 plus and Fe2 plus. So that is going to be it. Okay. I mean, I just wanted to clear all the confusions, all the doubts about how to write Kc, because that's the number one mistake. You make a mistake there, everything, the whole question gets messed up. Reda, just quickly, let me check your answer. Reda, why isn't the charge over there? I mean, it's Fe3 plus. You have to write the charge. So just make sure that the charge is written. I said now the other thing about Kc. Okay, just the other thing about Kc is that you must know that you'll be asked to you'll be asked to calculate the units for Kc. I say you'll be asked to calculate the unit for Kc. That's the second thing. So that's part one. Any question about Kc, that's going to be part one. This is going to be part two. You're going to be asked to calculate the unit for Kc. Now the C in Kc stands for concentration. Remember, the C in Kc stands for concentration, and the expressions that we just wrote down, like for example this one. Hopefully in physics you've probably studied homogeneous equations, I think, where you have to calculate units. In the same way, you have to calculate the unit for Kc. Every time the unit is going to be different. Uh, it depends on the expression. If the expression is different, the unit is going to be different as well. What is the unit for concentration? Concentration is mole per dm cube. So the top, so it's going to be mole per dm cube squared. At the bottom, what's the unit for concentration of N2? That's also mole per dm cube. And for H2, the concentration is again mole per dm cube, but this time it's going to be cubed. So it's going to be cubed. And you have to simplify this. Now the only thing is that it's actually kind of harder to simplify this. What you can usually do is you can take x as being equal to mole per dm cube. So this makes the whole expression much simpler. It's going to be x squared divided by x into x cubed. And if you simplify this, it comes out to be x to the power minus 2. That's it. And you can substitute what x was. X was mole per dm cube. So it's basically mole per dm cube. Or we can, instead of mole per dm cube, we can write mole and dm minus 3. And this whole thing is raised to the power minus 2. So this is going to be your expression, mole dm minus, and you can further simplify this. It's going to be mole minus 2 and dm6. That's going to be the unit for Kc in this particular example that we just did. So remember, instead of actually simplifying mole per dm cube and squaring and cubing and multiplying and dividing, substitute mole per dm cube with x. So it's going to be x squared divided by x into x cube. And whatever you're going to get, substitute mole per dm cube back again, and you're going to solve, and that will give you the unit for Kc. Is this part clear? Yes or no? Is this clear? Nee, this one. I mean, what is mole per dm cube? Mole per dm cube is mole divided by dm cube, right? I mean, this is mole per dm cube. So, Jida, you got this? I mean, if you bring dm cube to the top, it becomes -3. Okay, usually a lot of times. I mean, you can write it both ways. It's the same thing. So I think we're going to continue with this tomorrow then in the next class. Okay. Okay. Take care. Allah Hafiz.